Also within the category of covalent compounds are these things called giant covalent or network covalent compounds. Some examples are silicon, silicon dioxide, and carbon, which comes in a variety of forms. I'll talk about the different forms of carbon in a minute. But in a giant covalent compound, what we have is, not surprisingly, covalent bonds, but they go throughout the whole structure. And since they go throughout the whole structure, meaning every atom is connected to another atom and there's no break between them, it forms a huge molecule. If you want to think of a diamond can be thought of as one single solitary molecule. Here's why. This would be the structure that forms in a diamond. We have one carbon, and that carbon is attached to four other carbons. And each carbon is attached to four other carbons. And so we have the strong tetrahedral structure, and covalent bonds, which are stronger than ionic bonds and go throughout the entire structure. Another example is SiO2. This would be SiO2 in the quartz form. There's some more amorphous forms rather than crystalline, but that would be an example. And you'll notice that there's no point where you can say this is the molecule. But if you look at the proportions, you'll find that the ratio of silicone to oxygen is a 1:2 ratio. Therefore, when we write the formula, we write it as SiO2. Giant covalent compounds have some not very surprising qualities. If you think about a diamond, you can tell me that you know these things are very hard, usually. You also will know that they have very high melting points. If you could melt a diamond, it wouldn't be worth very much. Additionally, to having very high melting points and being very hard, they're also not going to dissolve in water. Better word to use here would be not soluble in water. Now, as for whether they conduct electricity or not, some do and some don't. We will talk about that in more detail under allotropes of carbon.